we'll start recording. So welcome everybody who's joining us on YouTube. And what we're going to do is we're going to revisit and answer some questions about the project. So our self-portrait that we have here. So we had two questions. So, you know, how do we know if we get the curved lines correct? And then also when you have short hair, what might you do to help that? Okay, so I'm going to see on my computer here if I have some images. So I have a really old picture of my daughter. So we'll load that up and we'll see if we can use that to answer some questions. Okay. All right, so I'm gonna share a new screen here and we can see this. All right, so Karina, can you see this image right here?
Yes.
My terrified daughter. So this is when she was probably about 1. But right, so here's her face. So in this picture she has short hair, and then we'll see if we can get some of these curves. So what might we do? What might we do with this hair? So probably what I would do is, you know, what I see here is like there's a little bit of a wave, you know, so we might be able to do something with trigonometric functions. Kayla, you're okay. So we might be able to do like some sort of wavy thing going on here, or you know, we might be able to just sort of trace the outline. So Nick, are you worried like, so I don't remember exactly. So my hair, I would just, for me, I guess I'm pretty bald, but a little bit of hair there. I probably just wouldn't put anything, right? I would just sort of make it so there's nothing on the top of my head. But, all right, so if we're worried about these curves, so the thing that I think you can do the most with is to deal with right, so this is the vertex form of a quadratic equation. So what you would do is you would go around, and then if you wanted to pick a spot, so if I look sort of right here on Zoe's forehead, it seems like this outline right here may be a little bit of a parabola. So what I would want to do is I would want to go and find sort of what would the vertex be of that parabola. So I'm imagining sort of a parabola that goes in right here. And so the vertex would be somewhere right around this point, right? So I would want to go and sort of figure out what that point is. It seems like it's maybe like negative 0.05. And then the K value is maybe 2.4. And so when I add a slider, what I'm getting is I'm getting this parabola that would mark the top or that front of her hair there. And so when I have this A slider, I can sort of bend it around, and this would define sort of that swoop in her hair. And if I wanted to, you know, shift it up, I could move that K value up. And then what we'll do is we're playing around here to try to figure out sort of what the best fit would be. And so there's no wrong answer. So if you decided that it was this versus, you know, this, whichever one you choose is fine, right? We're getting sort of a reasonable estimate. So I could choose this here, and then if I wanted to put this in, I would put my 0.3 here. Okay, get rid of my slider. So this is now my equation. I could make this a plus as well. And then all I have to do is sort of cut off where I would want it to stop. So it seems like maybe 0.63 is my x coordinate here, and negative 0.58 is over here. right? So this could be sort of a reasonable start to sort of tracing Zoe's hair. And then what I would do is I would come down on this side, and if I wanted to, I could just make it straight down, right? It doesn't have to be perfect. So right, so notice how there's some of these hairs that are coming out underneath, right? We don't need to capture the image perfectly. So what I might do is just drop this line straight down. And so at this, right, so this is 0.68. So I would make a vertical line, x equals 0.68, right? So, and then I would have it go from, I would have to cut it off in the y direction now, right? So from 2.66, and then maybe I would want it to stop down here, 1.767. Okay, and so as I'm going around, I would just sort of trace the outline of her hair there, and that would sort of define what we were doing. So I'm gonna kick it back over to you both for a minute here and see if you have any questions about this.
No.
Yeah, so go ahead.
Oh no, it's fine. You can go.
All right. So my hair is kind of all down on my forehead in my picture. So, and it's more like vertical rather than horizontal across. So I'm not sure if I can really trace the outline very well, but you're saying just do the outline of the hair rather than trying to fill it in?
Yeah, you could do the outline. Do you feel comfortable sort of sharing? Do you want to bring it up and then sort of share your screen?
Not sure how to do screen sharing.
So if
I
you
could just do a video. Start
well,
the video.
so I stopped my screen sharing. So on the bottom, do you see the buttons that say like chat and there's
Meeting
like a
settings.
Well, are you on a laptop
iPad.
or?
I'm on an iPad.
Or an iPad. So I'm not sure where they are on the
there's
iPad.
a share content. Would that be it?
Yeah, maybe try that. Yeah.
All right. So if I pull up my Desmos and then press share content.
We'll see. Yeah. We'll see what happens.
All right.
I know you wanted that too. Did that work out yet?
Hang on. Yeah.
Not seeing anything here.
Let's try this.
So alternatively, you could email me your link, and then I could bring.
Yeah, it says only the host can share in this meeting.
Okay.
I mean, I could just start the video and you'd be able to see my face.
All right. So try it again.
All right. Okay, let's see. Or maybe a website URL.
I can just change the settings so that you should be able to share.
Yeah, now I've got to figure out the best way to do it. I have a photo here. Should have photos.
Well, Nick's figuring that out. Carrie, does this help you out sort of that it doesn't really have to be
There we go. Is that it?
Yep, I can see your picture here.
All right. Yeah, that's not the Zoom thing, but
okay. So I think what you might be able to get away with is so I can draw on here. So what I would do is sort of like trace the outline of your hair, something like this, right? So it's probably going to look a little bit weird. So you would have something like this, right, that you would trace, and then you could put in like either segments of hair that went like this. So this would probably be a lot of lines, but if you wanted to give some sort of hair texture, you could do, something like this.
Okay.
So did you see the image, the one that I shared? I think it was example 4. And so example 4 was it had a lot of the hair textures in there with a lot of different functions. So
I think so.
So that was there's a lot going on in that one. So let me see if I can bring it up here. So you can all see my screen
Yep.
now. All right, so let's bring up our Play-Doh page. So I'm going to go ahead and log in here. All right, so I think it's in week March 13th to 27th, example portrait number 4. So we'll bring this one up to share. So can you see this now?
Yeah.
So see, like the hair textures, they're just a bunch of they're a bunch of lines. They're all shifted down a little bit as they went across. And so you can see when you zoom out, it looks pretty hair-like to me, like it looks pretty good. And so if you wanted to do something similar, you can see here that she didn't trace the outline. She just sort of added a bunch of lines in there. These are all parabolas. But you could do something similar where you just sort of look at the direction that your hair is going and then do a bunch of those if you wanted it to look pretty realistic.
Okay.
Right. So to me, when I like this one, I think looks pretty realistic with the hair. I think is pretty cool. So does that help out?
Yeah, I think so.
All right. And so Carrie, what's going to happen is it doesn't, just keep in mind, it doesn't have to be perfect, right? So we're not looking for like a perfect, a perfect example. And so some of these other ones, they aren't totally perfect, right? So you can see the hair here, there's just tracing an outline. So it's really up to the level of detail that you want to present, right? So this one was, the more lines that you put into it, the more detail you're going to get, right? So this is at 80 lines. So I said the minimum I wanted was 75 just to have some detail. And then this one is really super detailed, but you can see it's over 400 lines. So it doesn't have to be this detailed. This is one example that I show. I think there's some techniques in here, like with the hair, that are pretty nice to see. But it could be like this, right? So this one's 80 lines just over, and then you can see sort of the outline is traced here. And I think this one as well, right? So just over 80 lines, and we just get the outline. Okay, and so you can even see like over here, it's not totally perfect, and that's okay. Right, but I think what you'll find is at the end of it, it's probably gonna look like you. You'll be able to recognize yourself from it, which I think is pretty neat. All right, so other questions? Did this sort of help out in your journey with the project?
I think I'm all set with questions.
Yeah, me too.
Okay, so next thing on my agenda, I'm gonna switch back here. So let's jump back over to Play-Doh. So in our activities, right, so we can go here to our activities. What I wanted everybody to be doing was, we did last time we looked at exponent rules, and so now we're thinking about exponential functions. So we sort of talked through what what an exponential function is, what it looks like, and we have these two parameters. A, it gives us our initial condition, so this would be like our y-intercept, and then B, it tells us, hey, this is our growth rate, right? How fast is our function growing? And what we noticed was if this number is bigger than 1, right, we get this characteristic swooping up, right? So when B is bigger than 1, right, you're going to get a graph that looks something like this, and that when B is when B is less than 1, but bigger than 0, you're going to get a graph that looks something like this. Okay, so we sort of had these ideas from Tuesday, and now what we're going to focus on today is this, right? So given 2 data points, how do we find the equation of the exponential function that goes through those 2 points? All right. So on Tuesday we worked through this example. So we'll go ahead and we'll jump in and think about this example now, right? So we'll go and see if we can keep going with this process and figure out, hey, what is the exponential equation that goes through these 2 points? So I'm going to bring it back over to our virtual Blackboard here, and so I can use that a little bit better. All right, so the data that we're given in this example was, hey, we have two data points. We have 3, 4.5, right? So we're going to have this x value is 3, y value is 4.5, and then we'll have another data point which is x value is 5, y value is 10.125. And what we want to do is we want to think about, hey, how can we find an equation that has the form we want? Okay, so I'm going to make this slide a little bit better. And so the equation that we want to have something of this form: f of t is equal to a times b raised to the t power. Okay, so just that same form for exponential functions. And so what I need to do is I need to figure out what a has to be and what the value of b is. So the value of a and the value of b. So what I like to do is I like to bring this back and think about when we were doing linear functions. When we were figuring out a linear function, what we needed to do is we often found our slope, and then we found our y-intercept. So we had these 2 parameters that we were dealing with. And then, so those were m and b. And then in this case, we have these a and b parameters, right? So our initial condition and then our growth rate. And so what this tells me is, if I read this, is that this is really of the form 3, f of 3, right? So whenever I plug in 3, my output should be 4.5. Okay, so what I get from this data is that, hey, f of 3, when I plug in 3, the answer to that should be 4.5. But if I plug 3 into this equation over here, I also get, hey, this should be a times b cubed equals 4.5. Okay, so just from this one data point, the information that I get is I get that this equation has to be satisfied. A times b cubed has to be 4.5. And then similarly for this one, we would get, right, when I plug in 5, I would get a times b to the 5th. And I know that that has to be equal to 10.125. Okay. And so I have now what I'm given is these two equations. that I have to work with. Okay, so this is similar to what we did last time, except I set these equations up for you, right? So in the notes in question 2, I set up these two equations. And then in question 3, I just gave you the data points. And sort of this is the process that we use to figure out from our data points, how do we get these equations? Okay. So what I'm going to do is I'm going to put this up here. So we have these two equations. And now we're going to work through and see, hey, how do I put them together to get a exponential equation? So the first thing I'm going to do is I look at the side of the equations that has our variables in it. Okay, and what I want to do is I want to divide these two. So by dividing them, some nice stuff is going to happen. I'm going to be able to cancel my A's, right? A's are going to go away. And then my B's are going to be able to be combined using exponent rules. Okay, so I'm going to have something like this. I'm going to write AB to the 5th divided by AB cubed. Okay. So it doesn't matter which order you use here. Personally, I always try to put the bigger exponent on top just so it avoids a step later on where we don't need negative exponents. So we can keep all our exponents positive through this. So the bigger one I always put up on the top. And then what I know is that A times B to the 5th has to be 10.125, right? So that comes from this, right? So A times B to the 5th is 10.125. That's how I get this part right here. And then AB cubed has to be 4.5. Okay, so I'm just going to end up dividing these two equations. And then, so that comes from this part over here, right? So A times B cubed is 4.5. And so that's how I get that 4.5 down on the bottom. All right, so now all that work that we did with exponent rules is gonna come into play here. So these A's are gonna cancel, right? So I'm gonna divide the same thing. And then when I look at this part right here, I have B to the 5th over B cubed. When I put those two things together, I know they have 5 B's on top, 3 on the bottom. So I'm gonna subtract my exponents. So I get, this ends up simplifying down to B squared, okay? So we get B squared is equal to, and now we have this 10.125 divided by 4.5. So what I'm going to do is we can go over to Desmos. You can really use any calculator that you want. You'll have Desmos up, but if you wanted to simplify this, right, so you can do 10.125 divided by 4.5 and see what you get. Okay, so what we end up with is 2.25 as our answer. So if B squared is 2.25, then taking the square root of both sides gives me what I want. Okay, so clean this up a little bit. So B is the square root of 2.25. Okay, so far so good?
Yes.
Yeah? Yeah, okay. All right, so this is our B value. And now what we have to do is we have to take all of this and we have to then find our A value, okay? Oops. So we have B is 2.25. And now what I can do, if we come back up here to the top, I'm going to go ahead and I'm going to take B as the square root of 2.25 and I'm going to plug it in to either of these equations. It doesn't matter which one. So either one is fine. So what we'll end up with here is I'm going to go ahead and plug it into the first one. So we're going to get A times B cubed is 4.5. Okay. And so what's going to happen is inside of here, our B value, we computed it to be the square root of 2.25. Okay, so now I have this equation, a times the square root of 2.25 cubed is 4.5. And so solving for a gives me this. A is 4.5 divided by the square root of 2.25 cubed. Okay, so this is my a value and my b value. And now what we'll do is we'll take these expressions, and I'm going to bring up our Desmos window so we can, see what these numbers end up being. Okay, so let me switch here really quickly. All right, so you see the Desmos window now?
Yes.
So we had this, b is the square root of 2.25, and a was 4.5 divided by the square root of 2.25, and this was cubed. Okay, so this is our a value and our b value, and then if we wanted to, we could view them in Desmos as fractions. So it turns out that a is 4/3 and b is 3/2. So I could then look at my equation, f of x is equal to a, which is 4/3, times b, which is 3/2. Okay, I'm gonna write it like this, 3/2 to the x. Okay. And so we can see that this defines an exponential equation. We can see it growing. And then in our activities, right, so if we go back to our notes, our points were this: 3, 4.5, 5, 10.125. So we'll go ahead and put those back in. Okay, so I can get this here. 3, 4.5. That's on our exponential function. And then 5, 10.125. All right, so when I look at this, we can see that verifiably, I took my 2 data points. These are the 2 that I wanted. And then we walked through our procedure to get this equation, and visually we see that, yes, it does work, right? So this is an exponential function that goes through the 2 points that I wanted initially. Okay, so through the use of exponent rules and then some algebra, we're able to figure out this model. Okay, so this was a what we would call like an exercise, right? So we just gave 2 data points, but we can actually use this in a little bit more general setting. So what we can do is, in my notes here, I have this activity, right, where what we're going to do is we're going to look at the number of Facebook users and over time. Okay, so what we're looking at here is right. So this is in millions. So what this is saying to you, right? So this 10-1 means there are 1 million users. So this is a 1 is a 1 million. And then each of these is months. So 12 months later. So from December 2004, this is December of 2005. This would be December 2006. Then 4 months later, and then 6 months later, 10 months later, and so on. Okay, so at home, what you can do is, this is a live link. So if we click on this, it will bring us to some Facebook data. Okay, so what I've done for us is I took that chart and I plotted it in Desmos, and we can see, right, so if we zoom out, if we look at this data, we see that characteristic swoop up, right? So it's kind of growing like this. And that looks like an exponential function to me, right? So if you look at this data, just the shape of this, that feels like an exponential function. And so what we want to do is we want to use this process that we just figured out to see if we can model this data find an exponential function that kind of looks like this. All right, so what we could do is you get to choose. You can pick any two data points that you want, right? So you could pick, say, the first one and the last one, or you could pick two in the middle. You could pick sort of two at the end if you wanted to do something like that. And see if you can use this, right? So see if you can figure out what is the exponential equation that goes through those 2 points, and then compare it to this, or we can compare it to this data. What do y'all think? You wanna throw out a point? So Carrie, why don't you pick a point, and then Nick, why don't you pick a point on this from this data?
59, 150.
So you're gonna pick this one, 59, 150.
Yes.
Okay.
10, 1.
All right. So 10, 1 and 59, 150. Right. So those are our data points. And so let's see if we can walk through this and figure out what the exponential equation is that goes through those two data points. Okay, so let's jump back to our blackboard. All right, so I wrote down here your two data points that you both picked, and we're gonna model this, right? So we're gonna find the exponential equation that goes through these 2 points, and then we're gonna put it up on that data screen and see what we see.
Does it matter which order you put the 2 points in?
It actually doesn't, no.
Okay.
So what we're gonna do, remember the step where we divide the two equations? So we get to pick which one we want to be the numerator. So either order, you're gonna get to choose which one at that point anyways.
Okay.
Okay. All right, so again, we're looking for, this is our model, right? F of t is equal to a times b to the t. And then reading off this data right here, so reading off 10, 1, what that tells me is when I have an input of 10, I have an output of 1. So I would get this, a times b to the 10th is equal to 1. And then 59, 150, this says if I have an input of 59, so if I plug in 59 for my input, I'm going to get an output of 150. Okay, so we'll end up with something that looks like this. All right, so I'm going to go through and I'm going to do my division again. So I'm going to get a times b to the 59 equals 150. And then I'm going to divide on the left by a times b to the 10. And on the right, I'm going to divide by 1. Okay. So stuff happens. These cancel. And then any ideas what happens here? What am I left with?
B to the 49th.
Yeah, right. So we're going to subtract them, right? So you get b to the 49 is equal to 150. All right. So any ideas on how to solve this equation?
Take the 49th root of both sides.
That's right. So you could take the 49th root of both sides. That's pretty wild thing, right? But so in practice, taking the 49th root, so you might write it like this, right? You might write it like the 49th root of something. So we're not actually going to do that. What we're going to do is we're going to instead we're going to raise both sides to the 1 over 49. So in general, what I'm going to get over here is b to the 49th power. I'm going to raise to the 1 over 49. And then I'm going to do the same on the right-hand side. Okay, so remember that when we raise to a fractional power, this is the same as taking a root. And so instead of writing the 49th root with a little 49 inside of the square root symbol, we can use this exponent 1 over 49 to do all that work for us. And then on the left-hand side, 49 times 1 over 49 is just going to be 1. And so what we get is B is equal to 150 raised to the exponent 1 over 49. Okay. So far, so good? Or do we want to clarify that?
That makes sense.
All right. So if you want to see this more as a number that is more familiar to you, if you plug it into Desmos, this is approximately 1.1077. Okay. So these types of models, exponential models, are very, very sensitive to rounding. So when I do this workout, if I can, my preference is just to leave my answer like this, as B as 150 to the 1 over 49. And so that's going to give me the most accuracy as I can. So if I rounded it off to this, I'm going to get a slightly different model, and it's not going to be quite as accurate as I want it to be. So for our purposes here, what we're going to do is I'm going to leave B as this, as 150 to the 1 over 49. And so on WebWork, this is going to help you as well with you don't have to worry about how many decimal places, right, if you were just to leave it like this. Okay, so next step, what we're going to do is then I need to figure out what A is. So A times B to the 10th power, I know, is equal to 1. And then we said B is this 150 to the 1 over 49. So all I did here is, so I took this B in this equation right here, and I replaced it with 150 to the 1 over 49. Okay. And so if we keep going here, right, so what I'm going to do is this 10 right here gets multiplied by the 1 over 49. So I get A times 150 to the 10 over 49 is equal to 1. And then so A is 1 divided by 150 to the 10 over 49. And in this particular case, 1 over, we know that's a negative exponent. So this is 150 to the negative 10 over 49. So that's another one of our exponent rules. Okay, so here is my value for A, and then my value for B is 150 to the 1 over 49. Okay, so negative 10 over. I'm just putting this into Desmos really quickly, and then I'm going to bring us back over there. Okay. All right. So we have our data. Then we did some work on the blackboard to figure out that A is this value and B is this. And now, so if we look at our function, f of x equals A times B to the x, we get this exponential model. So if we check, so the data point that Nick chose was this 10, 1, right? So if I zoom in, we can see that, hey, yeah, it does go through that data point. And then, Carrie, you chose 59, 150. So it does, in fact, go through that data point. And, you know, it seems like a reasonable model, except these are a little bit off the end, right? So it's not a perfect model. And so if you went to predict this, right? So if you wanted to use this as a predictive tool, I'm not so sure that this model would be a very accurate one, right? So if I wanted to predict how many users we would have in the next month, the model would give us a prediction way up here, whereas that growth seems to be pretty unlikely. Okay, so what we're doing, and especially today, what we're seeing is people are making lots of predictions, right? So if you're keeping up with the news, you're probably hearing things like such and such organization predicts that we're going to have this many, viral cases at some point in time. And so what's happening in the background is people are running models just like this one here, right? So they're doing more sophisticated analysis than the one that we just did here with this Facebook data. But in our everyday lives, right? So it's particularly relevant to us right now, trying to stay informed of what's going on, to understand how these models are working. All right, so what I did is I've been sort of tracking the data for the growth of the number of COVID-19 cases in the US. So this is that actual data. So very similar to our Facebook data here, but it starts on March 10th, and then it goes out to, so this goes out to this morning, right? So I just put in the data from this morning, April 2nd. And so if you look at this, this looks like a pretty clean exponential model, right? So this looks like pretty exponential to us. And so doing a little bit more sophisticated analysis called a regression, this is something you would see in statistics. You can use an exponential model to look at the growth of the number of cases here. So if we wanted to predict what was going to happen tomorrow, right? So this is 23 days, right? So currently we are 23 days after March 10th, right? So that's what the 23 means here. And we have 216,000 cases. So if I wanted to predict, hey, what's going to happen on the next day, how many cases would we see tomorrow or next week or something? This line, this is a predictive line that says, hey, what are we going to have tomorrow? So this exponential model right here, so I'm going to put a little note in this. If the cases continue to grow exponentially, then our prediction would be tomorrow there would be 275,000 cases. Okay, and so I don't think we're in the exponential phase. I think we'll have a little bit slightly less than that. But there's another model that we're not going to spend a whole lot of time talking about it, but it's a logistic model, and the logistic model would predict that it's 233,000 cases tomorrow. So the logistic model looks something like this. So you can see that it fits the data pretty well, right? So a lot of the green points lie on this curve, and then the logistic model would predict that tomorrow there are 233,000 cases. And so over time, what we should see is the number of cases starts to slow down, right? So over time, it should start to slow. It shouldn't continue to grow at this rate. We should see that rate start to slow, and then what will happen is the number of cases will level off. And so with this data, just doing a logistic regression, we see that we would predict that the cases would level off somewhere around 330,000. Now, it's probably going to be a lot higher than that, because this is again not as sophisticated a model as other people are using. But what we can do, one of the ways that we can consider this data is we can look at growth rates. Okay, so what was the percentage growth from the day before? So if we look at these numbers, what these labels that I put on here mean is, in order to go from 754 cases to 1,025 cases, what we did is we grew by 36% on that day. So there was a 36% growth here, 28%, 27%, 31%, 36%. And as time goes on, what we really want to see is we want to see those numbers start to go down. Okay, so you can see that over here, right, on March 9th, we have this growth rate of, we grew by 50% in one day, which is a lot. And so then these numbers start to go down over time, right? So you see 32%, 19%, 25, 24, 22, 19, 15, 15, 15, and 14. And so in this data, right, that we can collect and we can look at, what we're seeing is these are the effects of, I think these are the effects of social distancing that's happening, right? So we see these effects, these growth rates are starting to go down over time, which is something that we should feel hopeful about, right? So these is saying, hey, what we're doing is working, right? These growths are going down. And so hopefully what we see when we get more data tomorrow is that this is even less, okay? So in order to think about this, right, so these growth rates over a particular period in time, we want to go back, right? So we'll go back to our activities, right? So back to our book, and down in the bottom here, what we can do is we can look at sort of the average rate of change over particular intervals, right? So that's how we're getting that percentage growth, right? What was the average rate of change on that next interval, or how fast was the function changing at a particular point in time? Okay, and so this idea of figuring out how fast something is changing, what is the growth rate, that is a lot of what calculus is about. So right now we're setting the stage, right? We're building up, we're preparing to go on to calculus. And so these ideas of average rate of change are particularly important. So for the end of this, right, so for the end of this section 5.2, I just want to take a moment and see if we can go back and think about that, compute these average rates of change, and then we can relate it back to something that we're seeing here, right? So these are how we're going to figure out, this is how I'm figuring out what these growth rates are that we want to see going down. All right, so I'm going to kick it back over to the two of you. What do you see here? Do you remember average rate of change?
It's change in output over change in input, right?
That's right. And so we have a formula for that, which is so we would have the average rate of change. I'm going to bring back up our Blackboard here. All right, so we're going to go through these four problems. So I don't know, Carrie, Nick, do you have this document up where you can see it?
Yes.
No, not right now.
Okay, so I'm going to jump back over to the Blackboard. I'll be able to see it as well, and I'll copy the problems down, but it might help if you have it as well. Okay. Just to remind us of the average rate of change. Okay, it was, as Nick said, right, so it's the change in output divided by the change in input. Okay, and so we can think about that, right? So this is very similar. We related this back to slope, right? What is the slope of a line? So how fast are our outputs changing compared to how fast our inputs are changing? And then if we think about it on a particular interval, right? So if we're changing on, say, from 0 to 1 or from 2 to 5, something like that, we would write this, right? We would look at it as f of b minus f of a, all divided by b minus a. Right, so you have a function f on this interval ab, right? So we'll put this up here at the top of the screen so we can all we have that in the back of our mind. And then what we want to do is we'll come over here, and then part A we can do together. What we want to think about, hey, what's the average rate of change of this function 2 to the x on the interval, say 0, 1. Okay, so as we're going along, right? So this is our A, and this is B. Okay, so when we think about this, right? So all our B's over here, these are our B's, and then these are our A's, right? So A is going to be 0. Anytime we see an A, we're going to have a 0, Then anytime we have a b, it's going to be a 1. All right, so if I compute my average rate of change, it's going to be f of 1 minus f of 0, all divided by 1 minus 0. Okay, feels pretty good?
Mm-hmm.
All right, so now to get f of 1, the next step is I need to come over here and say, hey, all right, so I have f of 1, right? I'm thinking about this one right now. I'm going to go ahead and I need to take this 1, right? So this is going to be a 1, and I need to plug it in up here. Right, so f of 1 is going to be 2 raised to the 1, and then f of 0 is going to be 2 raised to the 0, right? And this is all going to be over 1 minus 0. So 2 to the 1 is 2, 2 to the 0 is 1, and then the denominator is the same. And so what we get here is 2 minus 1 is 1, 1 minus 0 is 1, and so overall, right, our average rate of change on this interval for this function is 1. Right? So what we would see is the average rate that the function is changing is 1. Right? So we would expect that the next output to be 1 higher. Okay, so let's go ahead. So on the next page right here, so I'm gonna give you both a minute to think about this. Right? So here's our function. G of x is 5 times 3 to the x, and the interval is 1, 2. So take a minute, think about this function. Right? What's the average rate of change of 5 times 3 to the x over the interval 1, 2? All right, so while you're both going here, I'm gonna set this up for us. All right, so did we get this far?
Yeah.
Yes.
Yeah, and then we need to plug in. So what did you get for G of 2?
45.
45. And then G of 1?
15.
15, right? So 45 minus 15 over 2 minus 1. And so this ends up being 30 over 1, which is 30. Right? So our average rate of change on that interval is 1. Right, so this is the same idea. What we're doing, right? So if we're taking our numbers, we're saying, hey, what was the percentage growth over that particular point in time? Okay, so is this okay for us? Did we feel good about this?
Mm-hmm.
Yes.
Harry, this is okay for you too?
Yeah.
Okay. So just to bring back our other data, right? So we're going to jump back over here to bring back our other data. So what we did in order to get this 1.14 is we did the same kind of computation, right? So I did 2.2. This is our f of b. Okay, so this would be 216,721. Right, that's our f of b minus, and then this is 189,618. Okay, where we take all that and we divide by 23 minus 22. Okay, so what we saw, right, what we're seeing here is the change here is a 27,000 person increase, right? So there's 27,000 more cases. And then so that's an increase of 14%, right? So what we did is this number increased by 14% in order to get to our 216,721. Okay, so we look at this. This is the total number of cases, right? So this would be how many we're changing by, and then this number is reporting that percentage change, right? So this is about 14% increase from one to the next.
So if you have, so you can compute average rate of change if you either have 2 points or if you have 1 point in a function, right?
You can, yeah. So you can compute average rate of change with 2 points, right? So right now you need any 2 data points. Yeah, so that's going to give you the average rate of change over that interval.
But you can also do it if you just have 1 point in a function like we just did with the problems.
Oh, I see what you're saying. So no. So I'm not giving you a point. What I'm giving you is an interval, right? So I'm giving you this interval from 22 to 23. So this is not the 0.01. It's x equals 1 or x equals 0 to x equals 1.
Oh, okay.
So what we're looking at is we are looking at we're looking down here and we're saying, hey, what happens when we travel from 22 to 23? Or
okay.
What happens when we're at 21 and we go out to 23, right? What would be the average rate of change? How fast is that function changing? Okay, and so what we want to see is we want to see those rates of change start to go down, right? So we want to see things start to grow slower. So we want to slow down the spread and slow down the growth. And then that's what these numbers are giving you right here, right? So you can see that while the absolute number of cases is going up, the rate is going down, which is a good sign. That's good. Okay. We want to be seeing that, right? So, yeah. So the rate going down, that's something to say, hey, this is a sign that things are getting better, right? So I think there's a long road ahead of us, but this is, I think, something to be hopeful about, right? So if we see earlier on, right, these numbers are much higher. The growth rates are much higher, right? So down here, things were going up, right? So at the beginning, right, these numbers are going up. They're getting higher, which is bad. And now, while we have more cases, the rate is going down, which is better, right? That's what we want to be seeing. So if you're worried about the social distancing, and I know it feels bad, but here in the data, right, this is something to be hopeful for, right? Things do seem to be improving over time. Oops. All right, so we've got about 10 minutes left. I want to point out another situation. So we've seen a couple different ways where we can use exponential growth models, right? So this was the Facebook population, right? We saw that this was exponential growth. We've seen it. We did a circles activity where, you know, the circles kept doubling over time. We did that last week. And so another place that we see exponential models is going to be in financial data. And so I put together a student loan activity. And so I know for me personally, I have a lot of student loans, and probably everybody out on YouTube or, you know, anybody who's going to college, a lot of us do have student loans. And so I think it's valuable to realize, you know, sort of how they grow and sort of what do the interest rates mean for that. And so for the last 10 minutes, let's go ahead and think through this student loan growth activity. And so when I was putting this together a couple of years ago, these numbers, so $30,000 and 5.2% APY, these are the national averages. So a four-year college graduate coming out on average had $30,000 in student loan debt, and they were earning about an average of 5.2% APY. So the APY stands for annual percentage yield. And so you can think of this as, hey, after 1 year, right? So if I had this $30,000 and I made no payments, 1 year later, I would have that amount of money would grow. It would be 5.2% more than it is now. Okay, so they take this 30,000 and it would grow. It would be 5.2% higher than it is now. Okay, and so what we want to do is we want to think about this and say, hey, if I had $30,000 and I made no payments, how much money would I owe at the end of the year? So when you graduate, there's a very common thing where you can have what's called a deferral, so that you can defer some of your loan payments off for a period of time. And so to put it in a realistic sense, right, it's possible that you're offered a 1 year deferral. And so this would be a way to sort of calculate, well, what would that deferral cost you? All right, so if you made no payments for a whole year and your APY was 5.2%. So any ideas, Carrie or Nick? What do you think? How much money would you owe after 1 year if it's increased by 5.2%?
Maybe like around 31,600 or 700, maybe.
And so how did you compute that?
So 5% of 30,000 is about 1,500, and then you just add that on.
All right, so you did 5% of 30,000.
Yeah, because I'm doing it in my head, so it's just guessing.
Okay. So let's do it in the calculator. What we want? We want 5.2%. So how would we get that exactly 5.2% from 30,000? Carrie, do you have any ideas what you would think about? So we have this 5.2% that we're thinking about.
No.
So when we're thinking about percentages, let's see if I can. This off here. So when we're thinking about percentages, we can think about this. All right, so we're gonna have 5.2%, right? So 5.2% here, and what we're gonna do is when we think about percentages, this is like 5.2 out of 100, right? If you want to think about it that way. And so you can think about this as, hey, it's 5.2 parts out of 100. And if I do that, divided by 100, you may have thought like, hey, this is the same as moving the decimal point left 2 places. So this is 0.052. Okay, so 5.2%, when I click over here, it should be 0.052. So if I do this 5.2 over 100, right, we see this right here. This is 0.052. And so if I multiply this 0.052, right, what we would get is, hey, it's about $1,560. Okay, so at the end of the year, we're gonna owe $1,560 more dollars than we did before. Okay, so that would be at the end of year 1. And so what would happen? What would be the total amount that we owed? We still there?
Yeah.
What would be the total amount that we owed?
31,560.
Yeah, so at year 0, we owed 30,000. One, two, three. Desmos doesn't like commas. And then we'd have 31,560, right? So we'd have something like this. So let's put our axes back in here. And so we have these data points, right? So at year 0, we leave school, we have 30,000, we didn't make any payments. Now we owe 31,560. So if we continue going, right, so if I add this, what did we get here? We got, right, so our formula was, we did this 30,000 times 0.052, and then we added 30,000 to that, right? And that's how we got our number. So what would we do at the end of, let's say we got a 2-year deferral, right? So at the end of our first year, we owe 31,560. At the end of year 2, what are we gonna owe?
5.2% times 31,560.
Yeah, so you do 31,560. Again, you're doing like this, 0.052 plus
30,000, or no, 31,560.
Yeah, 31,560. So you could do something like this, right? Okay.
Mm-hmm.
So we should see here, it's 33,201.12. Okay. We do that, right? So we're going to see something that looks like this. Okay, so what I want to point out is what we can do is I can actually factor out this 30,000. And so 31,560, this is going to be the same as 30,000 times 1 plus 0.052. Okay, so we have this, and this is 1.052. Okay, so instead of adding on the 30,000, what I did is this 1 right here is incorporating that, adding on the 30,000. And so we have this times 1.052. So what I want to do is I'm going to replace my 30,000 times 31,560 with this expression down here. I want to see sort of what happens, right? So we can do the same thing down here, same thing that we did above first, and I should see that these numbers are the same, right? So 33,201.12. So what I'm going to do is I'm going to swap out my 31,560 for this number. And what do you notice in here? I have 1.052 times 1.052, and another way to write this would be 1.052 squared, like this. Okay. So what we get is here, this is 30,000 30,000 times 1.052 and 30,000 times 1.052 squared. So for the third one, we should see that our formula is 30,000 times 1.052 cubed. Okay. And then for the fourth, we'd have 30,000 times 1.052 the fourth. Okay, and so let's look at our data here. Okay. And so what do we see? What does this look like?
It honestly kind of looks linear.
Looks linear, right? So these changes are pretty close to one another. So let's keep going here, right? So let's do 5, and then we could have the same thing, right? So this would be raised to the 5th power, and then 6th, and then this would be the same thing raised to the 6th power, and 7. This would be the same thing raised to the 7th power, right? Still looks pretty linear, okay? So if we look at our function, right? If we look at f of x equals 30,000 times 1.052 to the x, right? When we zoom out here, we can see that they fall on this exponential, right? So they fall on this exponential curve. So when we model loan growth, we're also going to see this exponential growth here as things track over time, right? So when we come back over here, when we look at some of our questions, right? So we wrote down our function, and then we can predict, right? So how much we would owe after 15, 25, and 30 years by looking at these equations, right? So we could look at f of 15, right? F of 20, right? So it seems like after 20 years, we would owe $80,000. So I don't know about you, but there are, there's lots of people out there that have to pay on their loans over 20 or 25 years. And so you can see this exponential growth is going to really catch up there. Okay, so where we're going, this is going to be the end of our exponential functions. And next week, we're going to start logarithms. There's one question here that is going to be really hard for us to answer, which is, how long does it take for our amount to grow to $80,000, right? So how would we solve this question? So right now, what we're seeing is, hey, f of 20 is almost 80,000, and then f of 19 is a little bit less than 80,000. And if we wanted to be more precise than that, how would we go about doing it, right? So how could we get sort of an exact answer to this question? Now, one way to do that would be to use a calculator and say, hey, if I graph y equals 80,000, I could get a more precise answer computationally by looking at something like this. Hey, after 19.348 years, right, we would get this. But again, right, so if we need more precision than that, we're going to be in trouble. So the tool that we're going to use to solve equations like this, right? So how do we solve exponential equations? That tool is going to be called a logarithm. Okay, so next week we're going to start in on chapter 6, and we're going to think about logarithmic functions. So, all right. So over the weekend, right? So we have our Desmos self-portrait that's due, and then we have a homework over exponential functions that's due on WebWork. So be sure to submit those. But Carrie, any questions before we sign off here?
I don't think so.
I'm good.
You're good, Carrie?
Yeah.
All right. Well, if anything comes up with the self-portrait, or if anything comes up with Desmos, or with WebWork, just let me know. Send me an email, and then we can help that way. Well, we're gonna sign off here. So I hope you all stay safe and healthy, and we'll see you See you next week on Tuesday where we talk about logarithms.
All right. Thank you.
You're welcome. Bye.
Bye.